Okay, so let us learn a little bit about equilibrium. A lot of times, kinetics and equilibrium are like kind of lumped together. They are not the same thing. So before, when we were talking about kinetics,
Hi, Court.
you did leave your lunchbox in here. Kinetics is the study of the speed of a reaction. Equilibrium, on the other hand, is what we, so there are different ways that we can use the word equilibrium in like life, but in chemistry, when we're talking about equilibrium, we're talking about the extent of a reaction. So what does that actually mean? It means, will the reactants be used up to make products? Or are our reactants not capable of making products at all? I'm going to call that, are our reactants lazy? Do they just not want to react? Some chemical equations are like that. Okay, so how do we know if a reaction will make products or not? There's a way that we can quantify that, and it's called the equilibrium constant. The equilibrium constant has an abbreviation, so you don't have to write out equilibrium constant every single time. It's not like the rate where we have to write the word rate every time. The equilibrium constant has the abbreviation capital K, and then a lot of times it'll have the small letters E and Q as the subscript. There are other forms of K. We will talk about the KSP later on. When you get to organic chemistry, or I'm sorry, AP chemistry, we'll talk about the KP, we'll talk about the KA. All of these little letters just describe to you what kind of equilibrium constant it is. If you see big K though, that's your dead giveaway that you've got the equilibrium constant. So the equilibrium constant is a numerical value, and it will give you information to know if you've got lazy reactants or very hard-working reactants. Okay, so I'm going to show you how to calculate the equilibrium constant. Oh, am I okay to move on?
No.
Okay. It is the same for every reaction. So very much like the rate law, once you know how to do one, you know how to do all of them. And because of that, I think it's fun and easy. So here we go. I'm going to give you our pretend chemical reaction again. My D got a little bit out of control. I apologize. All right, so when we're writing K, we're always going to have products on the top divided by reactants on the bottom. What do those square brackets mean? Concentration. Okay, so here we go. I'm going to put the products on top. And now here, this is where it gets a little confusing because this looks an awful lot already like the rate law. You have exponents again, but now your exponents are found from stoichiometry, which makes it pretty simple. If you've got a balanced chemical equation, you can write the equilibrium constant for anything. Now I'm going to write it in red, and usually red means, you know, is the color of death, so be paying attention. solids and liquids, are not included in the KEQ. They're not included in any K. Why is that? Solids have infinite concentration. They're not dissolved in anything. They're pure. Pure liquids also are not dissolved in anything. Their concentration is infinity. And so you know from math that we don't ever want to do any math with zeros, and we don't want to do any math with the number infinity because it's not possible. So in order for us to deal with the fact that the math is impossible, we just don't do it.
I can't read what you have beside the K in that.
EQ.
Okay, thank you.
You're welcome. Okay, so let's do some examples of this. Can I move to the next slide? Okay. Joseph, are you ready for me to move?
Yep.
Okay. I just want to make sure that I'm not going too quickly. Okay, so let's start with this equation. Here I have just like my most basic acid-base equation. States of matter here are going to be important because it's going to tell us what things we can leave out of the K. Is this reaction balanced?
Nope.
It is.
Oh yeah.
It is. All right, so before I do anything, I'm going to check to make sure that there are, I'm just going to check to see what the states of matter are. So here I see that I've got a liquid. So I'm just going to put like a little line through it, like not super big because I want to make sure that I don't forget it exists in this chemical equation, but I'm going to put that line there so that I know, don't write it in the KEQ. Okay, so then KEQ equals only one product, but I have to keep both of my reactants. So HCl and NaOH. Now, I don't have to write any exponents here because I don't have any numbers that are other than 1 in the stoichiometric coefficients. So this is my final answer for KEQ. How was this? Thumbs up, thumbs down, thumbs medium? Okay, good, good, good. Let me give you another one. I'm making this up as I go along. So I'm going to go back and add my states of matter here in a minute. Okay, so copy down this chemical equation and then ask yourself, is this balanced? Is it? Not like this, it's not, right?
Try it on one side, one on the other.
There, that looks good then. Okay. Are there any things that we can leave out of the KEQ? No solids, no liquids. So we can leave out one of those products again. It's always nice when you can leave one out because then you don't have to do as much work. Okay, so again, I have only one product. and 2 reactants. But now, do you see NaOH has a stoichiometric coefficient there that's not 1? So I'm going to have to include that 2 as my exponent for NaOH. And that's my answer. How was that? Okay, good. All right, let me give you another one. I've already balanced it for you. Try to write KEQ on your own. So the first 2 questions you should always ask yourself are, A, is it balanced? Which it is. And B, are there any liquids or solids that I can leave out? There is a liquid you can leave out. Okay, so what does this do? There are no products. If there are no products, or no reactants, you will put a 1 in that place. Now H2 is pretty simple because it should just be H2 with its square brackets. O2 is a little bit messy because his stoichiometric coefficient is 1/2. So how do we do that? Just put a 1/2 there. So the exponent 1/2 really does also mean, like if you were in math land, this is what it would mean, right? But we're not going to write that here because that's going to make the look of our thing so much messier than this. So we're just going to leave it as the 1/2 and hope that we don't ever have to do any of the math there. All right, so now let me give you another one. It's already balanced. That's your first question. Your second question should be, are there any liquids or solids? Are there?
I don't have an idea.
You don't find any?
I don't have an idea.
Oh, are there any liquids or solids? So are there any L's or S's? Yeah, there's this one. So we're not going to have any reactants. That means we won't have anything as the denominator here. Okay, so now just like I said to you last class, if you see a charge on something, if something is an ion, you have to leave that charge there. So you cannot just write K here. It has to be K plus, otherwise it's not right. As well as SO4, that also needs to keep its 2 minus. And so here, this is my final answer. I could, if I wanted to, write my numerator is the same, and I could write that over 1 if I wanted to, but I don't need to, so I don't, because I'm lazy. All right, thumbs up, thumbs down, thumbs medium. How do you feel about writing equilibrium constants? It's fun and easy, right?
Disturbingly, it makes me nervous.
It's disturbingly fun.
Disturbingly simple, it makes me nervous.
Yep, I agree with you.
Yeah, that can be a thing. I feel like, especially like when things get more complicated, I feel like the majority of mistakes that students make are from overcomplicating things. because you get you like are very cynical of how easy it can't be this easy. Okay, so remember what I said earlier. K is a numerical value, and we can, by knowing what K is, determine whether or not reactants will be used to make products, or if our reactants are lazy, if they're just not going to do anything. So let's talk about what K actually means. So there are like really 3 different values for K. So here I'm going to label the first one. If K is large, what does that mean? All right, so to explain this, I'm going to write down like what the equilibrium constant, what a K, well, how do we actually calculate K? All right, so if I'm saying that this value is large, it means that it's like large. So I'm talking like 1 times 10 to the 4 and up, which 1 times 10 to the 4 is 10,000. Like that's a pretty decent sized number. Oh, no, no. If somebody offered you $10,000, that would be a lot of money, right? You could buy a fairly decent car with 10 grand. My husband has never bought lottery tickets before. He bought a Powerball ticket the other night. And then last night he comes to my room, he goes, "Would it surprise you to know that we are not billionaires?" And I was like, yeah, nope, it would not surprise me to know that this get out. So then he's like, yeah, nobody won the Powerball, so I'm gonna buy another one on Saturday. Oh my gosh. He's like a mini Dawson Wheelist. That boy is like gambling all the time. Okay, shh, I shouldn't have said that on the thing. Like not for real though. Okay, so what does it mean for that number to be large?
My aunt bought one of the Powerballs, like
For last night, yeah.
Yeah, and she was 1 number away from winning.
Yeah, see, that's why I don't think I could ever do it, because like the agony of defeat would be like, if you don't buy one, there's like no, you don't get any of your hopes up at all, because I'm 100 buy one, I don't care. Okay, so in order for this number to be large, what does the math have to mean here? It means that you have to have a large amount of products produced, but then also a small amount of reactants left. If that's true, and this is what our chemical reaction looks like, it means that your reaction will make a lot of products. So well, how do we describe that? We say that this reaction is product favored. It means that all things considered, when these reactants combine together, when they're exposed to each other, they will almost all be used up to make products. We also say that that means that if the reactants are used up, that the reaction goes to completion. In other words, the reactants will keep reacting until they're gone, or like most of them are gone. There might be some like little molecules left, but for the most part, they're gone and they've made products. Okay, so if this is true, the opposite is also true. If K is small, and we mean small, so like 1 times 10 to the minus 4 and less. So if K is large means that it's product favored. What would you suspect is favored if K is small? Yep. So if this is the case, it means that your reactants really don't want to mix at all. An excellent example of this is gold reacting with oxygen to form gold oxide. So anytime you have a metal oxide, that's what we would think of as rust or tarnish. You know what happens to copper if it's like, if you have a copper roof or something, or copper, and it's exposed to the elements outside, it turns green. Yep. So the rust on copper is called patina. The rust on, or like the oxide for iron is called rust. The oxide for silver is called tarnish. So do any of you guys wear like real silver jewelry? Some of you do. And so it doesn't like stay shiny and beautiful forever. You have to polish it and clean it every once in a while, because when it's exposed to like water and air, or if you wear it in the pool, it's not going to like break down the silver. It just forms a layer of oxide on top of it. And then you have to take that off. Gold doesn't really tarnish like at all. Its actual equilibrium constant value is something like 1 × 10⁻⁻60. That's a really small number. That means there are 59 zeros in front of this 1. And so that just means that this is a reaction that doesn't really happen, which is nice, because if you have gold jewelry, then you don't have to like clean it the same way that you would the silver jewelry. A reaction that is an example of K being large is the reaction of sodium metal or potassium metal with water. That reaction has a K value of something like 1 × 10⁻30. And so an example of this would be when my dad flushed that bit of solid sodium metal down the toilet. It was the perfect time, because all of his weapon that he used to destroy this toilet was completely used up in the reaction. And so when they were trying to investigate why this toilet had exploded from the wall of the bathroom, there was no evidence, literally, because every single bit of it reacted and was gone.
Okay.
All right, so I will give you a new homework, but not until Tuesday. Your homework that I gave you on kinetics is due on Tuesday. A lot of you have most of that done. It shouldn't take you very long. You can come today or tomorrow in JetBlock to get it checked if you like. And that's it.